Hi everybody, my name is Nico Heizmann. I am a PhD student of Uta Freiberg at the TU here in Chemnitz, and the topic of my talk today is internal diffusion limited aggregation on the Sierpinski gasket. And I want to start off with a little motivation, or rather how Meekin and Deutsch introduced the ideal A model in 1986 as a model for chemical annihilation processes. One example for such a process is electropolishing. And in electropolishing, one has a metallic object with a rather rough surface. And then electropolishing removes this roughness, and this results in a smoother and therefore more shiny surface. How is this done? The workpiece is immersed in an electrolyte, shown in blue here, and serves itself as the anode. Then a cathode is put in the electrolyte as well, illustrated in red here. And then current passes from the cathode to the surface of the metal, where material is oxidized and dissolved into the electrolyte. We view this as particles traveling from the cathode to the surface, where they remove some material. Like this. One mathematical model for such a process is the IDLA, or internal diffusion limited aggregation model. And for this, we will work on nice graphs. And by nice graphs, I mean locally finite and connected, such as the grid on the left-hand side, for example. On a graph, we will always introduce a special vertex, denoted by this white circle here. And this will be the place where the particles start. So this will act like the anode, like the cathode in our electropolishing process. So we will start consecutively simple random walks, which are the particles in the electropolishing example. And they are consecutively developed until they visit a previously unvisited vertex. So this is a vertex which is not inside the cluster already. Then the random walk is stopped, and this vertex is added to the cluster. So the first particle starts as an active particle in our specified origin, illustrated in red here, but this immediately stops and is added to the cluster, since the origin is not inside the cluster already. Then the second particle starts in the origin as well, makes exactly one random step, and this vertex is then added to the cluster as well. Same goes for the third in this special case. Now, suppose we already have an existing cluster. Again, particles start at the origin, and once it exits the cluster, it stops and is added to the cluster. So for the mathematical definition, let script I of k be the ideal A cluster after k particles have been settled. Clearly, I of 1 is just the origin, as we just elaborated. And the kth cluster is obtained as the union of I of k minus 1 together with the random walk xk stopped upon exiting the k minus first cluster, which is at the time sigma k here. So we assume the simple random walks xk to be independent, and sigma k is the usual exit time of the k minus first cluster. Okay. A topic of interest are the geometric properties of these clusters for large k. How does such a cluster look like? And this depends heavily on the underlying graph we're working on. And we want to start by discussing two results on the lattice, which is naturally the first graph one wants to look at things, right? And to provide some intuition, we start with another short simulation. So this clearly looks like ball in Euclidean distance on Z2, right? So let's denote the ball of radius n around the vertex x by bx of n and its volume by small bn. Recall that the cluster after bn particles is denoted by script I of bn, and It turns out that our intuition is actually true. In 1992, Lawler, Bramson, and Griffith proved this. The cluster is essentially a ball. For any epsilon, we have that almost surely a ball of radius slightly less than n, precisely n times 1 minus epsilon, is contained in the cluster, here in red. And the cluster itself is contained in a slightly bigger ball, namely a ball with radius n times 1 plus epsilon, here in yellow. Now we are also interested in how far can the cluster diverge from this typical shape. Later in 2013, Asella and Gaudier and independently Jerrison, Levine, and Sheffield improved this result by giving explicit bounds on fluctuations from this basic shape of a ball. Namely, for large enough n, the cluster after Bn walks will not differ more than the logarithm of n times a constant from this ball. Yes. Next, let's look at a different graph. Remember our motivational example of electropolishing rough surfaces. One way of modeling roughness are fractal sets whose Hausdorff dimension can be non-integer. We will look at a graph that approximates a typical fractal, namely the Sierpinski gasket, and we'll call this graph the Sierpinski graph, which is then defined by the typical self-similarity of fractals, or in this case of the Sierpinski gasket. So for the definition, we start with an equilateral triangle, and in each step we will copy the current graph twice and add these new copies to the right and top corner of the already existing graph, like so. Now this procedure is repeated. We again copy the whole graph and add the two copies on the right on the board, and on the top. And now this is done infinitely many times, and we define the resulting limit graph as the Sierpinski graph, which looks similar to this, but is of course an infinite graph. Our specified vertex where particles will start is on the bottom left here, which is also now illustrated in this white circle here. Okay, so this is the graph we are now interested in. And let's start again with a small simulation. And we can see that the cluster is spread very evenly over the copies. And actually this grows according to a ball as well, just in a different metric. In this case, the balls are defined with respect to the graph matrix, which is the dx of y here. And yeah, the usual graph metric is just the shortest path distance between two vertices. Again, Bn is now the volume of the ball of radius n around the origin. And the ideal A cluster, again, denoted by script I. In a 2020 paper Shen, Hus, Savahus, and Teplayev showed that this basic shell of the cluster is indeed a ball in this metric. In red and yellow, you can see the inner and outer boundary ball, how the inner and outer boundary balls look like in this case. Yeah. And in my recent result, we improved the result by giving bounds on the fluctuations from the cluster. Here the cluster does not diverge more than the square root of n times the logarithm from a ball of radius n to the inside. However, the outside bound is slightly worse. Here we only have n to the power of 0.815 times the square root of a logarithm. The powers of the logarithm actually can be improved, but they are negligible since they are not the dominant terms. Simulations lead to the conjecture that there are even better bounds. But this can't be achieved with the classical approach of Lawler, which was used here. Okay, so this concludes my talk. I hope I could give you some ideas about my research. If you have any questions, I would be glad to answer them. And thank you for your attention.